Welcome to the course Digital Filter Design. This course will be delivered by myself, Parnashree Chakravarti, R. Anita, S. Anusuya, Assistant Professor, EC Department, BSA Crescent Institute of Science and Technology. The objectives of this course are to strengthen students' knowledge of DSP fundamentals and familiarize them with the filter design concept. To develop IAR filter design methods based on mapping continuous filters to the discrete domain, to learn how to design FIR filters for the given frequency specifications using windowing technique, and also to implement digital filter design in MATLAB. The outline of the course are brief overview of filter basics, design of discrete time IAR filters from continuous time filters, and design of FIR filters by windowing technique. Before going to the detailed filter design, let me give you brief introduction about the filtering techniques. So, what do you mean by filter? So, in signal processing, the function of a filter is to remove unwanted part of the signal such as random noise, or to extract useful part of the signal such as the components lying within a certain frequency range. So, coming to the filters, the filter can be broadly classified into analog filters and digital filters. So, in case of analog filters, the input, output, components and applications, I'll be giving you brief introduction, and then I'll be talking about digital filters. So in case of analog filter, the inputs are electrical voltage or current. Mainly we are getting those kind of inputs from sensor. Then the components, the filter components required to design analog filters are mostly resistors, capacitors, inductors, op-amps, etc. The output of the analog filter is again electrical voltage or current. The applications of analog filters are in noise reduction, video signal enhancement, graphic equalizers, etc. Coming to the digital filter, the input should be in digital form, so we need ADC because all the natural signals are analog in nature and the analog signal cannot be given to the digital filters directly. So we need to convert the analog signal into digital, so we need ADC, then we get the digital input and that digital input is given to the filters. The components here are adders, multipliers, delay elements, etc. The output of digital filters are filtered samples, which is digital output. The digital output again can be converted to analog output by using the DAC. Applications of digital filters, again similar to analog filters, they can be used for noise reduction, video signal enhancement, graphic equalizers, and apart from this, any kind of signal and image processing applications, digital filters are used. Based on the frequency response, the filters can be classified as low pass filter, high pass filter, band pass filter and band stop filter, which is shown in this slide. So in low pass filter, it allows only the lower frequency components, whereas it rejects all higher frequency components above the cutoff frequency omega c. In case of high pass filter, it allows the higher frequency components and stops the lower frequency components based on the cutoff frequency. The band pass filter, it allows a band of frequencies which is required. For example, we need to extract some frequency information from one range to the other range. In that case, we need the band pass filter. And band stop filter, whose characteristic is just complement of band pass filter. Importance of digital filters. So mainly the digital filters have two uses. They are signal separation and signal restoration. So what do you mean by signal separation? Signal separation is needed when a signal has been contaminated with interference, noise or any other signals. For example, imagine a device for measuring the electrical activity of a baby's heart while still in the womb. The raw signal will likely be corrupted by the breathing and heartbeat of mother. A filter might be used to separate these signals so that they can be individually analyzed. Coming to the signal restoration, it is required when a signal has been distorted in some way. For example, an audio recording made with poor equipment may be filtered to better represent the sound as it actually occurred. So today we are going to discuss about the digital filter design. So the digital filter classes are FIR, which is nothing but finite impulse response filter, and IAR, infinite impulse response filter. So first we will be discussing the IAR filter and then we will be discussing the FIR filter, and with that along with that we will be giving the design problem, and the problems also will be solved using MATLAB. So coming to the IER filter, the IER filters are nothing but the filters whose response is considered as infinite, since there is feedback in the filter. So advantages of IER filters are they are very selective filters with few parameters. Then disadvantages are in general they are non-linear in phase and also unstable, and due to that disadvantage, the instability, we are moving to the FIR filter design. So far we have seen the introduction about digital filters. Now we will be seeing the problematic analysis of digital filter designs. When we are talking about digital filter design, first we should know what is digital filter. So we know about LTI system, linear time invariant system. So any LTI system can be considered as digital filter. So here you can see that I have written the LTI system whose impulse response is h of n. X of n is nothing but the input to the LTI system, and y of n is the output of LTI system. So if we consider this as a digital filter, what actually we are going to design here? We are going to design or find out the coefficients of this h of n. So what is this h of n? How we are going to find out? So it will be very clear if we see this input and output relation of LTI system. So here you can see that the output of LTI system, it is related to the input by the expression x of n, which is the linearly convolved with the sequence h of n. Once we take the dtft of the expression 1, we can see that here we are getting y of omega, which is equal to x of omega into h of omega. Why into? Because convolution in time domain corresponds to multiplication in frequency domain. Now if we take the ratio of y of omega to x of omega, we are getting here h of omega. What is this h of omega? This is nothing but the Fourier transform of h of n, which is nothing but the impulse response of the filter. So once we are finding the coefficients of h of n, that means we will be designing the filter. So filter design is nothing but finding the coefficients of h of n of the filter. If we see the difference equation of LTI system, we can write the output and input relation in this way, where this y of n is nothing but our output and x of n is input. So this is the difference equation which corresponds to the LTI system. So here if I break this summation from k equal to 0 to n to first term for k equal to 0, that is a naught y of n, and the remaining terms the right hand side similar thing. Then by setting this a naught equal to 1 or unity, we can get the expression as y of n equal to minus this plus bk into x of n minus k. So due to the presence of this term, that is nothing but our output y of n, it depends on the past outputs. That means it is the recursive system. So if we take the z transform of this expression, we'll be getting y of z for y of n, and y of n minus k is nothing but y of z into z power minus k. For this term we'll be getting x of z and z power minus k. So taking all the y term to the left hand side and x term to the right hand side, and by calculating the ratio, we'll be getting the ratio y of z to x of z, which is nothing but h of z, which is given in this form. So this is the form of IER filter or recursive system. IER filters are recursive system because the feedback is connected, or the output at present moment depends on the past outputs. Whereas in case of FIR filters, FIR digital filters, we are setting this term AK, k equal to 1 to n to 0, and we'll be getting the system function as h of z, which is equal to k equal to 0 to m bk z power minus k. So this is the system function of FIR filter or non-recursive system. We have seen the IER and FIR filter system function. Now we will be discussing the IER filter design in detail. So the IER filter design steps are only 2 steps. So first step is to design an analog filter which must be stable, and the second step is to convert the analog filter into digital filter. So these are the main 2 steps, but here these steps again contain some more sub steps which will be discussed later. Next, the types of IER filter. So we have the IER filter types. In that we have Butterworth filter, Chebyshev filter, elliptic filter as well as Bessel filter, but we are going to see here Butterworth filter design in detail. So once we know the Butterworth filter design, the remaining filter designs can be easily learned by the students. So first we are going to see the Butterworth filter. So what do you mean by Butterworth filter? How it is characterized? So the Butterworth filter can be characterized by its magnitude squared function or magnitude squared response, which can be given by h of j omega magnitude square, which is given in the form 1 divided by 1 plus omega by omega c whole power 2n, where this omega c is nothing but the cutoff frequency and n is nothing but the order of the filter. So as I said that first we'll be designing the Butterworth filter. So let us see first the properties of Butterworth filter. So the magnitude square response of Butterworth filter can be given in this form. Already we have seen that. So if we see this magnitude square response, this magnitude square response is monotonically decreasing function of omega. So that means if I draw here x-axis as omega and y-axis is h of j omega magnitude, the magnitude response is monotonically decreasing function of omega. Why? Because as the omega value increases, the value of h of j omega magnitude reduces. So second property is at omega equal to 0, when omega is equal to 0, its value is equal to 1. So the value is 1 here. And when omega equal to omega c, so when omega equal to omega c, the value is equal to 1 by root 2, or if we express this in dB scale, this is our minus 3 dB magnitude. Next here, this Butterworth filter, if we find the poles and zeros of Butterworth filter, there is all the poles of Butterworth filter will lie on the circumference of the circle, whereas zeros will lie at infinity. That means there is no zero. The Butterworth filters are also called as all pole filters. Coming to the specification of Butterworth filter. So first we will be discussing about the low pass Butterworth filter, because once the prototype low pass filter is designed, then any filter can be designed accordingly. So here this is the specification of Butterworth filter in terms of low pass filter in terms of gain. This is written in terms of ripple factor. So here you can see that the magnitude is written in the y-axis, x-axis it is written as omega, which is nothing but the angular frequency. So at omega equal to omega p, so omega p is nothing but the pass band frequency. So up to this the frequencies are passed, that is low pass filter, and omega s, after that it is stopped, the frequencies are stopped, so omega s is called stop band frequency. So here at omega p, the value of h of j omega magnitude is called as gain, which is nothing but the pass band gain, whereas at omega equal to omega s, which is nothing but the stop band frequency, the magnitude value is nothing but the gain, which is written in terms of denoted by k2. So here you can see that the k1 and k2, when it is expressed in dB scale, that is nothing but 20 log of h of j omega, where this h of j omega is considered at omega equal to omega p, whereas this k2 is 20 log of h of j omega, where omega is omega s. Now this is the specification when it is given for filter design in terms of gain. Now next is in terms of ripple factor. Sometime for designing the filter, the ripple factor's value will be given, but we need to convert it to gain, because all the filter design formulas, the n value, the order of the filter is given in terms of gain. For deriving the formula for order of the filter formula is given in terms of gain, and hence the analysis is easier when we write everything in terms of gain. So even if it is given the specification in terms of ripple factor or in terms of attenuation, we will be writing everything in terms of gain, so that it will be easy for us to design. So suppose now the specifications are given in terms of ripple factor, where you can see that at omega equal to omega p, the ripple factor here delta 1 is nothing but the pass band ripple. Pass band ripple is nothing but the fluctuation in the pass band, which is denoted by here as delta 1, whereas delta 2 is nothing but the stop band ripple. So the changes here in the amplitude is delta 1, the maximum amplitude is 1, so we can write this as 1 minus delta 1, whereas this is the stop band ripple. Now if we express this in terms of dB, now this K1, the gain in pass band, is given by 20 log of 1 minus del 1, whereas K2 is equal to 20 log of del 2, where all the logarithmic base, it is in 10 log. Base is 10. Now next we are going to see the specification of filters, digital filters, IR filter in terms of attenuation. So in terms of attenuation, so what is the relation between attenuation and gain? So we know that attenuation and gain, they are inversely related. So when we are talking about dB scale, my gain or attenuation, they are related as this way. So suppose let attenuation is in pass band, it is given as alpha p, whereas stop band attenuation is alpha s, then alpha p is nothing but minus of k1 and alpha s is minus of k2. So how they are related to gain? So attenuation and gain, they are having the inverse relationship in normal scale, whereas in dB scale we are writing this in terms of minus. So we have seen the specification of filters, IR filters, that is Butterworth low pass filter in terms of gain, in terms of ripple factor, as well as in terms of attenuation. So next we will be telling you the design steps for IR filter design.
So far we have seen the introduction of the Butterworth filter, and now we will move on to the design of low pass digital Butterworth IR filter. As it was discussed in the previous session, the design of digital filter comprises of two steps. The first step is to design the analog filter and the conversion from analog filter to digital filter. So these are the flow steps for designing the analog filter, and after designing the analog filter, it has to be converted into digital filter. The first step is to determine the order of the filter, which is given by the mathematical equation n is equivalent to log of 10 to the power of minus k1 by 10 minus 1 divided by 10 to the power of minus k2 by 10 minus 1. And next step is to round off the n to the next higher integer. As we increase the order of the filter, the response will be equivalent to the ideal frequency response. So and for that reason we are rounding off to the next higher integer. And the third step is to design to determine the cutoff frequency in terms of radians per second, and these are the mathematical relationship of the cutoff frequency and the passband frequency. So omega c is equivalent to omega p divided by 10 to the power of minus k1 by 10 minus 1 the whole power of 1 by 2n, and the same cutoff frequency can be expressed in terms of stop band frequency also. So omega c is equivalent to omega s divided by 10 to the power of minus k2 by 10 minus 1 the whole power of 1 by 2n. We can express any one of this way, either in terms of omega, that is passband frequency, or in terms of stop band frequency, or we can also take the average of these two frequencies. The next step is to determine the analog filter transfer function Hn of n, which is given by the relation Hn of n is equivalent to 1 divided by Bn of s. So this is a polynomial equation which will be discussed in the later on session. And the final step is to convert the normalized transfer function Hn of s to the unnormalized transfer function h of s. This normalized term is with respect to the 1 radian cutoff frequency 1 radians per second. after designing the analog filter transfer function, so now we need to convert that into a digital filter, because our ultimate aim is to design the digital Butterworth filter. So in order to convert from analog filter into a digital filter, there are two types of transformations. So one is the impulse invariant transformation, another one is a bilinear transformation. By any one of this transformation, we can convert the analog filter into digital filter.
Previous session we saw about how to design a Butterworth low pass filter. Continuation of that, in order to design a Butterworth filter, we have to check for different orders what is your poles and what is your transfer function. Let us consider there are two cases for Butterworth filter. One is a normalized Butterworth filter, other one is unnormalized Butterworth filter. So what's the difference between normalized Butterworth filter and unnormalized Butterworth filter is only the difference in terms of magnitude. For normalized, the value is 1. For unnormalized, the omega c, that is we have to calculate omega c value, that value to be replaced with SK formula. So let's see for different orders for normalized filter, for n is equal to 1 and 2. For a normalized filter, the generalized formula Sk is equal to 1 is a magnitude and other one is a phase. For pi k divided by n, for order is odd. For 2k plus 1 pi divided by n, for n is even. Then what is the limit of k? The k will remains in the range of 0 to 2n minus 1. You know what is n? N is a order. So what is the formula for unnormalized? The one have to be replaced with omega c. Let's derive the formula for Sk for order n is equal to 1. Sk is equal to, we'll take odd since n is odd. So pi k by n, where the limit of k is equal to, putting a 2 limit only, 1 is 0. Replace the n is equal to 1, the k value will become 1. There are two cases for k. One is k is equal to 0 and k is equal to 1. As we calculated the different k values, k equal to 0 and k equal to 1. So we got the solution S0 is equal to 0 and S1 is equal to minus 1. This value to be plotted in your S-plane graph. So we have taken a real value as well as the imaginary value. When you plot it, the S0 value lies towards your right side and S1 value will lies towards your left side. As we know very well, when the poles are lying in towards the left side will be a stable system. So we are going to consider only the value of S1. We are going to eliminate the value of S0. Next, we will calculate the polynomial function. The polynomial function formula is nothing but S minus S0 with a product of S minus S1 with a product of S minus S2, etc. What is this S0, S1, S2 is nothing but for the different value of k. So we have only one value, that is S1. So the Bn of S will become S plus 1. We are calculating for the first order. So it is nothing but B1 of S, which is equal to S plus 1. Why we have to calculate this polynomial is, from that we have to calculate the transfer function. So what's the relation between polynomial and transfer function is Hn of S is equal to 1 by Bn of S. So we know Bn of S formula, so it is nothing but 1 by S plus 1. So this is your transfer function for order n is equal to 1. Similarly, if you want to calculate for unnormalized filter, we have to replace the magnitude as omega c. So last we saw different value of n. So we started with n is equal to 1. We end up with the equation h of s is equal to 1 by s plus 1. The similar fashion, we are going to calculate the value of order n is equal to 2. Since we know the order n is equal to even, the formula for normalized filter Sk is equal to 2k plus 1 into pi divided by 2 into n. The value of n, the same limit 0 to 2n minus 1. So let us substitute the value of n is equal to 2 in this formula. For a different value of k, the k start with 0 to 2n minus 1, so it will go up to 3, 0 to 3. First we will calculate for S0 is equal to 0, putting in this formula. So the value is pi by 4. Similar fashion, put s is equal to 1. For different value of k is equal to 1. For n is equal to 2, the answer will become 3 pi by 4. Put k is equal to 2 in the same formula, the answer will become 5 pi by 4. Put k equal to 3, so it will become 6 plus 1, 7, 7 divided by 4, 7 pi by 4. So we got 4 different poles equation, S0, S1, S2 and S3. We have to check whether which pole will lies in the left side and which pole will lies right side. From that we'll came to know what is the stability. So which one will become a stable system. So before that we have to find the value of what is S1, S0. So S0 is equal to with the phase representation of pi by 4. So we'll replace e power j pi by 4. According to the formula it is cos pi by 4 plus j sin pi by 4. We calculate the different value for S1, S2, S3, S4. When we are plotting, the graph will come this way the value of S1, S0, S1, S2 and S3. So from it is very clear the 2 poles will lies towards your right side and 2 lies in towards the left side. So this will be your stable system. So we'll calculate for this what is your polynomial function and what is your transfer function. So put it in the B2 formula. Why it is a B2? Since we are going to calculate the order 2. So S minus S1, S minus S2. What happened S0 and S3? Since it lies in the right side, so we are going to eliminate it. When you are plotting, when you are simplifying this equation, the answer will become S square plus root 2S plus 1. So from that we are calculating what is your transfer function H2 of S, which is nothing but formula is 1 by B2 of S. The answer is 1 by S square plus root 2S plus 1. The similar fashion for any order we can calculate, just we have calculated only for 1 and 2. You can calculate for n equal to 3, 4, 5 and etc. in the same manner. Only the things you have to remember, whether n is a odd function or whether n is a even function.
In the previous session, I told the 2 transformation methodologies for designing the digital IAR filter. One among them is the impulse invariant transformation, and also I discussed about the flow steps for designing the digital IAR filter. After finding out the analog transfer function, the transfer function will be in the format of H of S is equivalent to K divided by S minus P1, S minus P2 multiplied by S minus Pn. So where P1, P2 and Pn stands for the poles. So by applying the partial fraction, the H of S has to be solved in such a way the transfer function should be in the format of C1 divided by S minus P1 plus C2 divided by S minus P2 plus so on Cn divided by S minus Pn, and this can be written as summation of k is equal to 1 to n Ck divided by S minus Pk, where C stands for the constants after applying the partial fraction. And by using the impulse invariant transformation, so this H of S can be transformed into digital transfer function H of Z, which can be represented in the format of summation k is equal to 1 to n Ck divided by 1 minus e to the power of Pk into t into z to the power of minus 1. So this is said to be like a unit delay element, and this Pk stands for the poles, which is equivalent to this, and Ck is nothing but a constant value. Now we will move on to the mathematical analysis of digital IAR filter design using impulse invariant transformation. Let us consider the specifications which is given in digital domain as the magnitude response value varies from 0.8 to 1 for the frequency range lying from 0 to 0.2 pi, and the magnitude response is less than or equivalent to 0.2 for the frequency values varying from 0.6 pi to pi. So mathematically this can be correlated as in the x-axis y, that is omega, and in the y-axis magnitude response, which is given as 1 to 0.8 for the frequency value omega p and less than or equivalent to 0.2 for the frequency value omega s. Hence the omega p value will be equivalent to omega, that is 0.2 pi, and omega s value will be equivalent to 0.6 pi. And we need to consider one more important point while discussing about the impulse invariant transformation, that is a relation between the analog frequency and the digital frequency. So this omega is said to be like a digital frequency, and this angular frequency is called as the analog frequency, which is given by the relation omega is equivalent to omega into t, where t stands for the sampling period. So according to that, the analog frequency is equivalent to omega p by t, and analog frequency, the stop band frequency is equivalent to omega s by t. So in the design procedure, all the parameters are represented in the analog domain for designing the analog filter, and then only we have to convert that analog design into analog transfer function into digital transfer function. So now we will see the mathematical analysis of digital filter using impulse invariant transformation. Let us consider the magnitude response in digital domain as The value of magnitude response varies from 0.8 to 1 for the frequency value 0 to 0.2 pi, and it is less than or equivalent to 0.2 for the frequency value vary from 0.6 pi to pi. When this is represented in a graphical form, so the x-axis is represented in x-axis omega is taken, and in the y-axis magnitude response is represented. So the value ranges from 1 to 0.8, and the corresponding frequency value is represented as omega p, and for the values less than 0.2, the corresponding frequency is represented as omega s. Hence 0.2 pi is equivalent to omega p, and 0.6 pi is equivalent to omega s. And in the design, as I told earlier, the first and foremost thing is we need to find the order of the filter. So the order of the filter is given by the formula n is equivalent to log of 10 to the power of minus k1 by 10 minus 1 divided by 10 to the power of minus k2 by 10 minus 1, the whole divided by twice the log of omega p by omega s. And all these parameters are represented in the analog domain and also in the form of gain, but the given specifications are in the digital domain. So we need to map the analog frequency with the digital frequency using the relation omega is equivalent to omega t, where this omega is represented as digital frequency and this omega is for the analog frequency. So the relation is omega p is equivalent to omega p by t, and omega s is equivalent to omega s by t. So based on that, the frequency will be equivalent to omega p is equivalent to omega by t. So it is equivalent to 0.2 pi by t is nothing but the sampling period, and let us assume t is equivalent to 1 second, so which is equivalent to 0.2 pi. And then the omega s is equivalent to omega s by t. Similarly, omega s is equivalent to 0.6 pi divided by t. Again I am taking the t value, sampling period value is equivalent to 1, so it is equivalent to 0.6 pi. And next, coming to the gain value. So all these values are represent the normal scale, but it has to be represented in form of gain. So to represent in form of gain, so k1 is equivalent to 20 log of the value, so it is equivalent to 0.8, so which will be equivalent to minus 1.94 dB approximately. And similarly, I need to find the value k2, which is equivalent to 20 log of 0.2, and when we apply in the calculator, it will be equivalent to minus 13.9 dB. So now we have to substitute this k1, k2, omega p and omega s in order to find the order value. So after substituting all the values in the order formula, it will be approximately equivalent to 1.68. And as I told earlier, the next step in the design is the order has to be rounded off to next higher integer. So we can take it as the order of the filter as 2. So n is equivalent to 2. Next, we have to determine the cutoff frequency omega c. So omega c, according to the formula, omega p divided by 10 to the power of minus k1 by 10 minus 1, the whole to the power of 1 divided by 2n. So we know all the values here, omega p, k1 and n value. Omega p value is equivalent to 0.2 pi and k1 is equivalent to minus 1.94, and order we have now found it as 2. So by substituting all these values, the omega c, that is cutoff frequency, will be equivalent to 0.725 radians per second. So now so far we have determined the parameters omega p, omega s, n and omega c. The next step is we need to determine the normalized transfer function h of s. So the relation is already given in the previous session. H of n is equivalent to 1 divided by polynomial function, that is Bn of s, and we know that order is equivalent to 2, that is n is equivalent to 2. So for n equivalent to 2, the transfer function normalized transfer function is given as 1 divided by s square plus root 2s plus 1. So the term normalization, that is normalized factor, indicates that cutoff frequency is assumed to be 1 radians per second. And after finding this normalized transfer function Hn of s, the next step is to find the unnormalized transfer function by considering the cutoff frequency according to the given specifications. So according to our given specifications, we have found that omega c is equivalent to 0.725 radians per second. So with this value, we need to substitute s is equivalent to s by omega c in the previous equation, that is in the normalized transfer function. So the unnormalized transfer function becomes as 1 divided by s, instead of s I have to replace it by s by omega c. So s divided by 0.725 the whole square plus root 2 s. So s divided by 0.725 plus 1. By solving these equations, we will get the final h of s is equivalent to 0.5256 divided by s square plus 1.025 s plus 0.5256. So this is the analog transfer function. So h of s is the analog transfer function, so which is given by this equation, and now we need to convert that into h of s, that is a digital transfer function using impulse invariant transformation. As I told earlier, by applying, when we go for the impulse invariant transformation, we have to apply the partial fractions. So before getting into the partial fraction, first we need to find the poles of this quadratic equation. So by solving this quadratic equation, we get the poles as these two factors. So s plus 0.512 minus j 0.512. Similarly, s plus 0.512 plus j 0.512. So this is the pole 1 and this is the pole 2. And now we will apply the partial fractions. Since we have two poles, we need to take the two constants. So c1 divided by the same denominator function plus c2 divided by same denominator function. By solving this equation, it is found that c1 and c2 values are equivalent to 0.5136j and 0.513 minus 0.5136j. So I am applying the constant values 0.5136j and the c2 value here, and the denominator function I am rewriting in the form as s minus of minus function. So s plus 0.512 becomes as s minus of minus 0.512 minus j 0.512, and again the second term minus of 0.5136j divided by s minus of minus 0.512 minus j 0.512. So this is in the form of the required format of the analog transfer function. So with this we can convert into h of z based on the transformation formula which I have already seen. So summation k is equal to 1 to n ck divided by 1 minus e to the power of pk into t into z inverse. So this is a transformation formula. So in the place of p, we have the two parameters. That is, this is your P1 and this is the P2. The same we need to apply over here. So C, instead of C, the numerator constant we need to apply. So 0.5136j divided by 1 minus of, this is the pole 1. The pole 1 is written here. So pole 1 into t into z inverse. I'm assuming t, the sampling period as 1 second. Similarly, you apply the same thing for the second term. So C2, that is nothing but 0.5136j divided by 1 minus e to the power of minus P2. The P2 is the second term, minus 0.512 minus j 0.512. So that I am applying over here. So finally, after solving this entire equation, the h of z results as that is 0.301 z inverse divided by 1 minus 1.044 z inverse plus 0.36 z power minus 2. So this is our required digital filter transfer function. So from this we can plot the response for the digital filter. Thank you.